All right. So yeah, just to solidify what I did just before the break. So I'm going to take these n-fold matrices. So remember, I get an n-fold matrix by taking two fixed matrices A and B and stacking them many, many times. Yeah? And again, I mentioned to you that the examples of n-fold matrices are transportation problems with fixed number of factors. So for that kind of problem, you can do integer linear optimization in polynomial time. So that's already a special case of the theorem that I was mentioning to you. So there's more complicated optimization problems you can do. I mentioned to you when you have one convex function and you have several fixed linear objective functions that you combine in this way. There has been recent work also on convex minimization, not just maximization, but minimization, applications to stochastic integer programming. I mean, in stochastic integer programs, there's a lot of matrices that have a special structure like this. You will see that in a moment. And yeah, again, if you want to make an analogy to what happens in the normal integer linear programming problems, so you have network flow problems, right? Network flow problems can be solved efficiently. So I think of these myself as some very nice family of nonlinear, I mean, it's convex nonlinear, but optimization problems where you have special structure on the matrix and then you can get nice results. Okay? So what I'm going to do in the second lecture is talk about the mathematics that is inside these problems. So how do I prove these kinds of theorems? So I'm not so interested in giving you every detail of the proof because you're going to fall asleep, okay? I want to tell you the main tools that work to prove these kinds of theorems because they require new mathematical structures. I mean, this is what I think is very interesting, okay? So I will talk about this, the mathematics that are used to prove these theorems. And I think even if you didn't understand any of the theorems, you should like this part. I mean, it's wake up again. I mean, this is not. So oops, no, I don't want to go there. I want to make it bigger. Okay, so let's talk about. So I want to start by talking about the mathematics that are necessary to prove these f-pitas. Yeah? So when you're approximating a nonlinear objective function, you want to maximize a nonlinear objective function by a sequence of approximations, yeah? That get very, very close to the optimum. Okay? So what kind of techniques do you use to do that? So I want to show you, all of you, a really, really clever way to encode the lattice points of a polyhedral region. So you have a polyhedral region, and normally people think of them as vectors, right? You have one vector with coordinates blah, 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 another vector, so it's a list of vectors, and that's a very inefficient way to represent them because there's exponentially many of them. So this gentleman is Alexander Barvinoch. He's at the University of Michigan, and he was the creator of a data structure, if you want to think about it, which is going to encode the lattice points. So let me tell you how you encode lattice points with this technology. So I'm going to do something that at the beginning looks really crazy. So I'm going to take a lattice point, and for each lattice point, associate a monomial. So for example, if you have the lattice point 7, 4, -3, this is going to be encoded in the monomial set 1 to the 7, set 2 to the 4, set 3 to the -3, okay? So this is every lattice point is a monomial. And now, you consider the sum of all possible monomials. So you have one monomial for each lattice point inside your set. So this is if your set is unbounded, this is a series, right? It's an infinite series because there's infinitely many lattice points. But if your set is a polytope, it's a bounded polyhedron, for example, this is a finite set, but it might be you may have a huge number of monomials. Okay, so here comes the theorem that is used to prove this multi-objective result as well. And so let's see. So here's the theorem. You have this huge polynomial of lattice points. There's one monomial for each lattice point. Well, guess what? If the number of variables is fixed, if the number of the dimension of the polyhedron you're working with is fixed, then there's a polynomial size representation of the same object as a rational function. It's going to be represented as a sum of rational functions. Remember, a rational function is a quotient of two polynomials. You divide one polynomial by another. And in fact, the polynomials are going to look like this. There's a monomial on top, and then in the denominator, there's going to be a product of binomials. So the binomials are going to look like 1 minus z to the bij. And remember, I'm using this kind of notation, okay? This is the monomial notation. So the theorem is, you start with a polyhedron in fixed dimension. And then you can compute a representation of the lattice points, of the sum of the lattice points, as a sum of rational functions with this kind of shape. So that's the theorem. I'm going to show you an example because if there's only one thing you learned today, I want you to understand this theorem. It's a really cool theorem. So here's an example. Let's take a square. It's a 5,000 by 5,000 square. So there's more than 25 million more lattice points inside this square. Yeah? So from here to here and from here to there. So for example, you have some place at this corner over there, you have the lattice point 5,000, 5,000, which is now a monomial, right? It's set 1 to the 5,000, set 2 to the 5,000. So you don't want to type these, right? I mean, nobody wants to type one by one all the monomials. For example, here's another monomial. The point of coordinates 1, 2 is right there. Set 1 to the 1, set 2 to the 2, right? So you don't want to type all of the 25 million ones. So what the theorem is telling you is that instead of typing 25 million monomials, because that's all the lattice points, you type just four rational functions. So these rational functions right there, there's 4 of them. Look, they are exactly of the shape I promised. The numerator is a single monomial, and the denominator is a product of binomials. Yeah? And if you do that, if you don't, okay, what you can do if you don't trust me is you can take this into Mathematica and Maple, assuming you have enough memory in your machine, and then say expand. And then what's going to happen is if you expand this, it's going to represent you 25 million monomials. It's a huge thing. With just 4 rational functions. So this is much better, right? That's what the theorem says. That you can represent in an efficient way this theorem. Let me tell you right away a tremendously beautiful corollary. Okay? Suppose you want to count the number of lattice points. So suppose you don't know the lattice points in advance. So you want to count the number of lattice points. Well, what I can do here, is substitute. So I can do the substitution set 1 equals 1, set 2 equals 1. I just substitute these two values. So what am I going to get? I get a 1 for each monomial, right? So that gives me exactly the number of lattice points if I take the sum. Now, of course, you tell me, well, but that's a big problem because you don't have this representation. So you have an object that is huge, but that's not the object you have. You have this other object, right? So can you substitute set 1 and set 2 equals 1 there? No, because there's a singularity. But you can use complex analysis. I mean, you can calculate residues, a residue calculation, or if you don't know any complex analysis, just think of that you're taking the limit. Yeah? And this will tell you exactly how many lattice points are there. So you have a representation. So remember, so the Barvinox theorem tells you that in polynomial time, you can compute the representation of all the lattice points that is short and compact. And then that means that in polynomial time, you can also compute how many lattice points are there as long as the dimension is fixed. This is a very non-trivial theorem. Okay? Is it clear? Okay. Sorry? Yeah, the polyhedron is given to you by linear inequalities in fixed dimension D. So let's say you promise me Bernard that you're only going to give me 100 variable polytopes. So yeah, then this will be polynomial time, but again, this will be the dimension will be in the exponent. So the higher dimension you go, things are going to turn out, bad. Any other question? Okay. I'm going to sketch the proof of Barvinock's theorem because I'm going to use it. I'm going to use Barvinock's theorem so this is the main engine, the main tool that you need to encode the Pareto optima, for example, to encode the optimal solutions of a nonlinear objective function. I'm going to explain how. Okay, so let's try to give a sketch of how one actually proves such a theorem. So I'm going to give you an idea of how one actually proves such a theorem. So first of all, if I want to prove this theorem for polytopes, I can reduce to the case of cones. Because as Tim explained, actually, Tim had this on his slides as well. You have a convex body. You can make a convex cone by just putting the convex body kind of in a higher, so you put it in one subspace, and then you create the cone from the origin. So I can deal with cones. First of all, that's the first step. And then the second step is that suppose I have a very special kind of cone. So this is what people in geometry call simple cones, because the number of rays, so it's a polyhedral cone, so that means that there's finitely many rays, and the number of rays you're going to have is equal to the dimension. For example, if it is two-dimensional, I have just 2 rays. Okay? So if I have such a cone, then I will tell you right away a formula for the lattice points as a rational function. Okay? Here it is. It's a cooking recipe, how you can cook this rational function. On the numerator, well, let me tell you the denominator first. The denominator is more natural. So the denominator, you take the rays of the cone are you can find an integer vector, because remember, everything is rational polytopes here. So you can find an integer vector that, it's an integer vector that tells you the direction of the ray. So let's call that C1, C2, CD. So these are the rays, the ray directions, okay? Now, in the numerator, so in the denominator, I'm going to have 1 minus z to the C1, 1 minus z to the C2, where these are the ray directions. And you might be, okay. So, and then in the numerator, I'm going to have the sum of the lattice points that lie in the fundamental parallelepiped. So what's a fundamental parallelepiped? Is the set of all lattice points that can be written as a linear combination of the rays with coefficients between 0 and 1. So look at the pink region. The pink region are all points in the cone, in this cone. There are linear combinations, but you have coefficients in the linear combination that are between 0 and 1. So that's very common. So this is the fundamental parallelepiped, and I just need the lattice points that are inside. So let's look at this example. So this is an example. Here's the origin, and the rays are, so this ray here is what? 4, negative 1. Yeah, this ray here is the vector given by the vector 4, negative 1. And this other ray is given by 1, 2. Yeah? And sure enough, in the denominator have 1 minus z1 to the, so this is 1, 2, right? Encoded as a monomial. And here I have 1 minus z1 to the 4, z2 to the minus 1. This is the other ray. Okay? And then here on top, in the numerator, I have 9 monomials because I have 9 lattice points inside the fundamental parallelepiped. Now, here's the amazing fact. You expand this rational function, and you're going to get infinitely many monomials, and each monomial corresponds to a lattice point here. Let me just say one reason why this is true. If you look at the denominator, let's look just at the denominator for a moment. What does that remind you of? This is the geometric series, right, that we learn in elementary calculus. Yeah, so the denominators are geometric series. So you have 1 over 1 minus z to the beta time, and then you raise this, so you expand this thing out. So what you're going to get, as you did in calculus, you're going to get 1, then you get set to the beta, then you get 2 times set to the 2 beta, then set to the 3 times beta, and so on. So this is a typical geometric series, right? So then you have another geometric series. That's for the other ray. So it's 1 over 1 minus set to the alpha, let's say. So again, you have another geometric series, which are just the multiples of alpha and beta. These are the linear multiples of alpha and beta. Yeah? So when you multiply them together, what are you going to get? You're going to get all possible ways to write something of the form, set to the c times alpha plus d times beta, right? Where c and d are non-negative integer multiples of these vectors. And that's how you get almost all the lattice points except the ones that are inside the fundamental parallelepiped. But that's why you need to multiply by the numerator. Is it clear? Just a taste of how you do it. Okay, so we know how to do it for simple cones. Okay. Now, this algorithm is very nice, and this algorithm is almost perfect, except that the number of lattice points on the numerator is too big. It's too big. There's too many lattice points there. It's not polynomial size. If you want a polynomial size representation, you need to make sure that the number of lattice points in the fundamental parallelepiped is a constant, or just one to be better, right? You just want one number, one lattice point. So that's what Barvinock called the unimodular cone. So I repeat, a unimodular cone is a simple cone that has just one lattice point in the fundamental parallelepiped. Okay? So that's his theorem. He can break, you give me any cone, and I can break it as a union and addition of unimodular cones. And there's polynomially many of them. So then that's exactly why the formula that I showed at the beginning is going to work. Okay? In the Barvinock formula, you had the sum was plus or minus, set to the ui, and then you had a product of 1 minus set to the vij, right? So you have some expression like this, and you have only one in the numerator, only one monomial in the numerator, precisely because a unimodular cone. So that's a magical thing. I'm not going to explain to you in the details how it works, but essentially, repeat the steps. You start with a polytope, turn it into a cone. Then you break it into cones that are simple. That means that the number of rays are as many as the dimension. So for example, here I went from a square cone to a cone broken into 2 triangles, right? And then, once you have such cones, you have to break them further until they have just one lattice point inside, in the fundamental parallelepiped. So think of this yellow cone, then you break it into smaller cones that have fewer lattice points, until you just have one lattice point, and then you're done. Are you with me? Questions so far? So this is how you prove Barvin, how do you compute Barvin algorithm? By the way, there's an implementation of everything I have told you. This is called Latte. There's software called Latte. You can download from UC Davis, and it implements the Barvinock algorithm. Yeah, okay. So now people are thinking, okay, you have this really awesome representation of the lattice points as a rational function, very compact. How do I use that to do optimization, right? How do I do? So let me just write the theorem again here. So on one hand, so it's a beautiful schizophrenic representation. So here I have the lattice points. So it's the sum of the lattice points set 1 to the alpha 1, set 2 to the alpha 2, set d to the alpha d. And you have this for every lattice point in the polytope. So it's a long sum, but you're representing this long sum as a plus-minus addition of rational functions. that look like this. Okay? So that's long. You don't want to deal with this. You have that. So how do I use that to do optimization? Well, I will tell you, first of all the calculations when you want to actually do evaluations, you will need to use residue calculations. You will need to use limits or complex analysis because you are going to evaluate everything on this side of the equation. You're not going to deal with this. You don't expand, because if you expand, you run into trouble. But now I need to play with these generating functions and get the value of my nonlinear objective function. So remember, my linear objective function was, my nonlinear objective function was f, was a polynomial in d variables. This is what I want to maximize. I want to find the maximum of this polynomial. So I'm going to do something that is really, really, really cute. I want to write another rational function like this one, but that represents not just the lattice points, but represents the evaluation of the lattice points of this function. So my new rational function has to be a way to write f of alpha. So the value of f of alpha is the value of the lattice points alpha inside for this function times c to the alpha for every lattice point. Okay? And here in this side of the equation, I need to have something like this. Okay, so finally, for that, derivatives are good for something. So let's take the derivative. So if you have a function like this, so this is a sum of monomials, and then you take a derivative with respect to one of the variables and multiply by the variable, then you get the same function, but multiply with the lattice point. You see? And so let's do an example here. So suppose this is just a one-dimensional example, just one variable. So the lattice points are 0, 1, 2, 3, 4. Take the derivative and multiply by the variable. So what do you get now in front? You get 1, 2, 3, 4, which were exactly the values of the function of the lattice point. You see? The coordinates of the lattice point. Now suppose you want to square this. So you want to evaluate the square. So x squared. That's your function f. Well, I'll apply the derivative twice. And then you will get the square of the lattice point. So this is the evaluation of the lattice point at the square. Yeah, so that's a differential operator that you can apply to the rational function. So if you you start with a rational function like the ones that I told you, but if you take the derivatives, if you apply this differential operator to the original Barvinock rational function, you're going to get exactly a new rational function that is slightly more complicated, but still it's essentially of the same shape. You see, the denominators are still rays of some cone. Yeah? The numerators are more complicated because you are taking derivatives and putting exponents that are not 1 in front. But this is how we encode all the values of the function f for any non-linear objective function f inside the generating function. Okay? Are you with me? Any questions so far? Okay. So yeah, so here is the lemma or the theorem that makes everything work. If you want to evaluate the lattice, the function f, the objective function f, on the lattice points, you just need to take the differential operator that looks like the polynomial f. Yeah? And this operation of doing you can do this in polynomial time in the degree of the polynomial and the input data. So to recover this rational function. So you recover the rational function from the Barvinock original computation, essentially. Okay? So that allows you to do the evaluation. Now, when you're doing multi-objective optimization, well, instead of having essentially instead of having just one value here, you can have several derivatives of different kinds. So instead of you can have a vector type evaluation. Okay, so one last piece of mathematics, and then everything will be done. So you have. So remember, you want to find the maximum. You want to find the infinity norm of the function f on all the lattice points. So let's say the lattice points are x1, x2, xn. So how do you do that? Well, I will consider the p norm. The p norm is taking the value of the function at the lattice point raised to the p power, and then taking the p root of that. So it is a well-known fact. I mean, you can check that when you do that, you do this to the k norm, so where you are taking k powers and then taking the k root, bounds below. So the k norm bounds above the infinity norm, which is the maximum that you want to compute, and this divided by the k root of the lattice points gives you a lower bound for the maximum. So these are the upper and the lower bounds that I promised to you, right? So these LP norms give you these bounds, the upper bound and the lower bound. And again, so you are doing the computation of these kinds of polynomials by dealing with the generating functions. Okay. Okay. I'm going to change topics completely. So maybe take a deep breath. Any questions? So because I'm going to talk. So if you didn't understand anything I said, wake up again. I'm going to talk about a different method to optimize, to do optimization. Yes.
So how do you compute these p norms of these rational expressions without expanding?
Yeah. So this polynomial. So the differential operator that I was using. If you have the differential operator of f, sorry, you just need to apply that to the p times, and that's you see. So that you don't need to expand f itself, which would be bad. You're right, because then you will have expansion of any monomials, perhaps. But here, you just apply the differential operator of set to f p times. So it's kind of multiplicative. Yes.
So what in the multi-objective case you were just regarding linear objectives?
Yes.
So why? I mean, it seems like higher degree does not do any harm to.
Well,
because you can do with.
So that is more technical, but so there we're going to use another technique of Barvinov, where we can actually recover projections of lattice points. So today, Tim was talking a lot about the issue of you have a set projects down. Is it still a semi-algebraic set? Here, when you project the lattice points of a polytope, the lattice points of the polytope project still into lattice points, clearly, if you do a linear projection with integer coefficients. But the tricky part is going to be making sure that which of the lattice points downstairs in the shadow are still integer. I mean, are still present. Not all of them will be hit. So that's why I didn't want to give all these details. But there's a more. You need an extra tool to get rid of this multivariate case. Essentially, even though there's linear, it's going to be more. It has a different kinds of problems. Yes.
I mean, if you want to decompose a simplicial code into unimodular codes, how many codes do you have, depending on the size of your?
Well, it depends on the. So you see that when you have a cone, the number of lattice points that you have in the fundamental parallelepiped is the determinant of the race. So it's.
You'll have at least this many.
Yes. So wait, no. You can do it. You can do it more efficiently. You can do it essentially in the logarithm of this. So let me show you. Let me show you. This is a really cool example. So let's take the vector 1, 0, and here I need 1k. Okay. So how many lattice points are there here in the fundamental parallelepiped of this cone? Let's just count them. How many are there? Well, there's 1, 1, 1, 2. So you have essentially all the way to 1, k minus 1, right? So you have,
And 0.
And 0, yes, of course, yes. You have 0. Yeah, that's the fundamental parallelepiped. Okay? I'm going to show you how to decompose this into 3 cones. 3 cones. Okay? Get ready. 3 unimodular cones. Oh, that's interesting. Okay, so here is my first cone. So I'm going to write this as the sum and addition and subtraction of just 3 cones. Okay, here it goes. First I need 1, 0, 0, 1. That's a unimodular cone because the fundamental parallelepiped of this has just the origin. That's 1. Okay. I have, you see this cone here, I can subtract that cone. So I remove the cone 1, 0, so 0, 0, 1, and 1, k. So I remove that cone. I subtract from this one, I subtract that. I'm not done yet. What am I missing? I subtracted too much this ray, so I need to add just the ray 1, k. You see? So even though the number of lattice points is k minus 1, you can do better. And that's the point here.
Logarithm of the number of logarithm.
Maybe rather than say, I don't say, there's an explicit bound that is really, really nice and it's much better than just the determinant. Yeah. Any other question? Okay, so we're going to start fresh. Wake up again. You don't need to understand anything that I said before. I'm going to talk about another mathematical technique that will allow me to talk about these n-fold matrices, optimization, integer optimization with matrices that have this nice structure in blocks. It's a block structure of these matrices. Okay? And I already mentioned that this allows you to prove some nice theorems. And so what is the technique that I'm going to use? It's not going to be Barvinock generating functions. It's something completely new, so you can really start fresh. That's based on so-called Graeber bases. This gentleman is Jack Graeber. He's still alive, huh? So you're learning fresh mathematics. So he's the inventor of this topic, 1975. All right. So what's a Graeber basis? So let's learn about Graeber bases. So you want to optimize a nice convex function, nice convex polynomial function, over the lattice points of a problem of the form ax equals bx non-negative. For example, think of the transportation problem if you want to have an example in your mind. So what Jack Graeber studied was the lattice solutions of the kernel. So he's looking at the set of integer solutions of the equation ax equals 0. Okay? So he's going to introduce a partial order on the kernel, on the integer kernel of this matrix. Okay, so I'm going to say that a vector u is conformally smaller than v if 2 things happen. First of all, they have the same sign pattern. They have the same sign pattern. And then when I look at the entry by entry in absolute value, the absolute value of ui is less than the absolute value of vi. For example, here's an example. 3, -2, -8, 0, 8 is less than, in this strange order, than 4, -3, -9, 0. Why? Because they have the same sign pattern. It's plus, minus, minus, plus, 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 minus, minus, plus, plus. You see, they have the same pattern. And if you look at an entry, say this one, this is 9, and the other one is 8 in absolute value. Okay, so that's the order that I'm making. It's a partial order on all possible infinite lattice solutions of the equation ax equals 0. So I'm doing linear algebra over the integers, okay? So now this other vector cannot be compared to these vectors. Why? Because it doesn't even have the same sign pattern. Okay? Now you're ready here's the definition of a Graeber basis. So a Graeber basis of a matrix is the set of minimal vectors on this order that are in the kernel of the matrix. Yeah? Yeah, so there must be some minimal elements, minimal under the support of this, under this order that I just defined for you. And for the experts, so for people that have worked before in integer programming or have taken an integer programming class, you may have heard about Hilbert basis. Well, a Graeber basis is just the Hilbert basis of the 2 to the n possible orthons intersected with AX equals 0. Okay? So if you have heard of Hilbert basis, Graeber bases contain all possible Hilbert bases. Here's an example. Here's an example. Take that my matrix A is 1, 2, 1. So that's a 1 by 3 matrix. And there's 8 elements in the Graeber basis, 8 of them. So you can check that these vectors that I have here and the negatives of these vectors are in the kernel of the matrix. If you multiply these with these, you get 0. Yeah? Now, I claim they are minimal in which sense? For example, if you take this vector here and you remove any of the entries that you have there, you are not going to get any of the non-zero entries. You're not going to get an element of the kernel anymore. Yeah? So these vectors are minimal in that sense. Yeah? They're minimal in the order that I just gave you. Okay, so how should you visualize the Graeber basis elements? So there's a very nice way to visualize this. So if you think of the integer problem, AX equals B, X non-negative, those are the lattice points inside a polytope, right? So but then you can think of the Graeber basis elements as some arrows or some directions that you connect one of the elements of one of the lattice point solutions here to another one. Why? Because the elements of the Graeber basis are elements of the kernel. So if you add them to the solution, you get the same answer, right? So all I'm saying is that if you have AX equals B, X non-negative, and then you have another Graeber basis that has the same sign pattern as this guy, then you're going to be okay. So you can add that AX plus G. This is in the kernel, so that's going to still give you B. And because it's the same sign pattern, you're going to have still the non-negativity constraint. Okay. So you can think of this as some kind of network connecting all the possible solutions. So in fact, that's exactly what Jack Graeber did in 1975. So he proved that if you have a Graeber basis for your problem, for your matrix A, is an optimality certificate. So either you found the optimal solution already, or you can find a Graeber basis element that gives you a better solution. Yeah. So you start in one integer solution, and if that's not the optimum, you can augment to a better solution. Yeah? You can augment to a better solution. And the moment you cannot augment anymore is because you have found the optimum already. So you are at the optimum. So that's the beautiful property that he proved for the linear case. Okay? It's very, if you like the simplex method, for example, this is something that you are going to like a lot too, because it's very reminiscent of the simplex method that you pivot from one solution to the next in a graph. Are you with me? Yeah? Is it okay? Okay, several people have worked on this. I mentioned several names, Raymond Hemeke and Shmulon. John Lee is not in the list, but he'll come up in a moment. Many people have come, Rekha Thomas, many people. So this is a very interesting topic. And I want to mention some facts, because that's essentially what makes this a very interesting area. Okay, so first of all, they're hard to compute. The Graeber bases are amazing, right? They can tell you the optimal solution of every problem of the form Ax equals b, no matter what right-hand side b you give me. So you see, it's a very general family of solution methods. So that don't depend on the right-hand side of the equation. Yeah? They don't depend on b. There's software to compute them. If you really want to compute an example, you should download the software 42. This software is really nice, and it has gone through several generations of development. Yeah, the name is supposed to be a joke. If you have read the right book, you will understand the joke. But anyway, see, this was started by Raymond Hemeke and Peter Malkin. They had a very nice development, and there's new versions of this software for computing Graeber bases. So did I run out of time?
No, you can. 2 minutes.
2 minutes, okay. So, okay, so let me just go through this slide, and then it's a good stop. So the other thing is that for people that like algebraic geometry, Graeber bases are a special case of Grobner bases. So if you have heard of Grobner bases, well, you're seeing one right now. So these are universal Grobner bases for a toric ideal. They generalize the circuits that we use in linear programming. So this is really a generalization of linear programming, because all the steps that you take in linear programming are essentially contained in the Graeber bases. Now the bad news is that Graeber bases are huge. In principle, these vector directions that you use to do the pivots, the augmentations, there can be too many of them. And in fact, it was proved that it's NP complete to decide whether you have already all of them. So for example, you may have computed 1,000 of them, and you don't know whether this is already finished or not. But in the rest, when we come back after the coffee break, the point that I want to make is that if you have a Graeber basis, then in general it's hopeless to compute Graeber bases. But if you have a very nice matrix, a highly structured matrix like the n-fold matrices, they can be computed efficiently, and then you can do all kinds of really cool stuff. So I guess that's it, right?
Okay, thanks.
Thank you.
It's not a coffee break, it's a tea break, I guess.
Ah, okay. Well.
And yeah, we will be here again at 4 for the third part of this lecture.